Hello and welcome to Func Prog Sweden. First, as always, I would like to thank all our recurring viewers. Welcome back to Func Prog Sweden. And to all new viewers and participants, welcome to Func Prog Sweden. This is the meetup where we explore functional programming. And we have had presentations in anything and everything from, believe it or not, C++, Java, Erlang, Haskell, Scala, Clojure, Rust, Dart, and more. And it doesn't matter if you're a functional programming expert or if you have never heard about it. You're warm welcome, and hopefully we'll learn something new today. With that said, let's head over to the agenda for today. First up, I'll do a short introduction by me, Magnus, and then we'll head over to Catch 'em All, Efficient Massive Tabular Data Handling with Tablecloth by May. After that, we go over to Rustland, an intro to Rust by Michael. And in the end, we'll head over to Darklang, a functional language for the cloud by Paul. And of course, as always, I'll do a short summary in the end. First up, I would like to thank our video sponsor, Adabeat. Adabeat is an IT consultancy company based in Stockholm, which have offices in Stockholm and Ho Chi Minh. And most of the developers have a functional programming background. If you want to know more about Adabeat, check them out in social media or on their webpage, adabeat.com. Then schedule the coming next meetup will be 18th of April, and then we'll run one in May and then one in June, which we haven't really put out any schedule for yet, so we'll come back with that. Then if you want to support the Func Prog Sweden community, head over to MeetUp and join the community, or follow us on the YouTube channel. And as of from January this year, we started up a Discord server, so check it out also and chat with other functional programmers. And if you really want to support the community, you can get a t-shirt like this in the Func Prog Sweden spread shop, so you can check out the link there. If you have questions during the presentations, please ask them in the YouTube chat or on the Discord server, and I will read them up to the presenters. With that said, let's get started and head over to our first presentation, Catch 'em All, Efficient Massive Tabular Data Handling with Tablecloth by May. Welcome, May.
Oh, happy to be here.
Hello. Hello. Welcome to Func Prog Sweden.
Yeah, I am super happy to be here. I am recording all the way from Israel, so cool.
Yes.
Okay, so should I start? What do you say?
Yeah. Lead it away.
All right. Now's an amazing time to start. So let's begin. Okay, so hi everyone. I am super excited about this meetup, and I'm so happy to have you all here. And let's begin. But one more thing before I actually start. Let me just do this. Okay. Yeah, so remember that this is a recorded session. So in case you missed something or you want to rewatch it again, the link will be available after this recording. And you can see I think in all of the slides, you will see my Twitter handle. That's not to get me famous. It's so it will be easy for you to reach out to me and ask more questions, or you can send me amazing Star Wars meme. That's always coming in welcomed. So 100 billions events per day. So when I worked at AppsFlyer, today I work at Forder as a DevOps engineer, but when I worked at AppsFlyer as backend developer, I had to do, or not alone, obviously, there were other developers there, but I had to handle 100 billion events per day and do massive data manipulation. And then I found, and the main development language was Clojure. And the reason for AppsFlyer choosing to work with Clojure as the main development language was the performance that Clojure brings with it. Now, here's the thing. When you get to a certain extent of performance of events, of number of events that you need to handle, this performance doesn't come just like this out of the box. You have to do some manipulation, you have to tweak some things, and then you start to do some profiling of your code and you ask yourself, how much time is spent in each function of the code? When does a thread wait on a lock? How much time does a certain thread or function spend on the CPU? So once you start to explore your code and look for the most consuming parts, then you understand that, okay, you need to do each and every part better, so it's going to take a lot of work. So when I encountered Tablecloth and what it has to offer, my mind was blown away. I am not a part of AppsFlyer anymore, but if I knew about Tablecloth back then, I would be stunned. So I think it's a good time to start. Yeah. All right. Let me present myself because that's important. So wait a minute, why is this getting stuck? Okay, so my name is Beisaron. I'm a software engineer. I am a DevOps engineer at Forder, and I'm writing in Clojure, Node.js, Groovy, Python, and literally any language that you bring up to my hands, I will say, yeah, I want to do it. I am an international public speaker. I do live coding. I do hands-on workshops. And the reason for the international part is because I love to do that wherever I'm invited to. I love traveling. So there you have it. Last thing is that I'm a sworn Star Wars fan. You can see the BB-8 rolling in the side, and that will be the last Star Wars thing in this presentation because we are in a Pokemon theme for today. So okay, let's talk about the agenda that we have. So the first thing that we will do is we will do a small introduction into Tablecloth. We will talk about what this library has to offer in terms of handling tabular data. And then we will talk about the Pokémon datasets, which I used for the code examples that we will see today. Then I will be comparing the same things that I can do in Tablecloth to other ways that I can do that in Clojure. And the last thing that we will do is we will take a deep dive into Tablecloth's main structures. So it will be helpful for us to better understand the way that Tablecloth works and how it's doing its magic. So let's begin with Intro to Tablecloth. So before I talk about Tablecloth, I have to start by presenting TechML dataset because Tablecloth is essentially a wrapper around TechML dataset. Now, TechML dataset was authored by Chris Nurenberger, and it is a Clojure library aimed for tabular data processing, just like Python's pandas, if you're familiar with it, or R's data.table. It supports pragmatic data-intensive work on the JVM by providing powerful abstractions. Now, as I said, the main goal of TechML dataset is efficiency and high performance, and there's a lot to say about this. And if you want to hear more from Chris himself, the author of TechML dataset, I highly recommend this talk that is presented over here. And you can see the QR code that if you point your phone directly at this slide, this QR code will take you to the link of this talk. And while you take this photo with of the QR code, I will say that I could have chosen a better screenshot of Chris's face, but I tried my hardest, and after a few times, I was like, okay, that's the way it is, and I send my love to Chris anyway. Okay, so let's talk about Tablecloth. As I said, Tablecloth is a wrapper around TechML dataset, but what is it exactly? So it's a Clojure library designed to make table processing performant, easy, and consistent. And This library was authored by GenerateMe, which is the GitHub handle of Tomasz, together with the Clojure community members who are still contributing to Tablecloth until this very day. Now, if we take a closer look at what I wrote here, when I said performant, easy, and consistent, then I want to say why I chose these specific words. So when you consider technical tools or library, I guess that you should always have in mind a few things, like memory usage, performance, is it cost effective, and developer enablement. And when I say developer enablement, I mean how much human time is invested in getting things done. Is it easy to use? So when I say performant, I mean both developer enablement, this is the kind of performance, and also performance as we all know. And I can assure you that Tablecloth provides both, but you know what? Don't take my word for it. Let's just see that in the next few slides. So, as I promised, we're going now into the Pokemon datasets. So, play with Pokemon datasets. We have for today 2 datasets that we're going to play with. Again, this QR code will lead you directly to the link of those datasets. So the first one, both, by the way, were taken from Kaggle, as I suggested here. The first one is the complete Pokemon dataset. Now, this dataset contains information on all 802 Pokemons from all 7 generations. Now, if I tell you the truth, I'm only very familiar with the Pokemons from the first generation. Don't ask me how old I am, but I welcome all of the 802 because, you know, it makes things much more interesting when you're trying to play with data. And this data set contains just Pokedex ID, height, weight, classifications, etc. The next data set that we have here is the combats data set. It contains information on Pokemon battles with the 2 Pokemons who participated in this battle and the winner Pokemon. Now, disclaimer, I don't know when or where these battles taken place at or when, but does it matter? I don't think so. Let's just have fun. Okay, so now what we will be doing is we're going to compare things that we can do Tablecloth to other ways to do the same exact thing in Clojure. Now, what I'm going to show you are simple actions that are kind of something that people do on their everyday job if they're handling data, like loading a CSV file and then using that as a map, like sorting. And the code that I'm going to show you in Clojure, maybe it's not the best code ever written in Clojure. Maybe you yourself can write it even better or nicer. But I want you to not focus on, the length or the way I wrote it and say, oh, I can do this better. I just want you to take the bigger picture and try to understand what these examples are here for. And let's just take a look and you'll see what I'm talking about. So the first example is how do we load a CSV file and then use it as a map? So we'll start with Tablecloth. That's it. Surprise! It's just one function that takes the file path of your CSV file, and then what you will get, the result of this function will actually return a data set, which is a structure that behaves like Clojure map, just a regular Clojure map. And if we want to do that in Clojure, that's the way it's done. And now you can say, well, maybe that's not so bad. It's just 3 lines compared to 1 line. That's not really bad. But wait, what you get back from using Reader is not a Clojure map. In order to get a Clojure map, and when I say Clojure map, I mean like the good old key values map. That's what you'll have to do. So you need to create an extra function to convert a vector of vectors into a vector of maps. Just the comment sounds kind of annoying, to be honest, but that's the way it is. So this is the first example. and see how short and fun and intuitive this dataset function in Tablecloth. I don't know. I loved it. So the next example that I think is pretty common for, in our everyday usage is finding the shortest something. Here, it's finding the shortest Pokemon. Oh, and I have to say this. Did you notice how I called it Code Wars? I was like, wink, wink, Star Wars, but it's still Pokemon themed. Okay, yeah, I thought it sounded funnier when I prepared the presentation, but okay. So let's see the example of how we can find the shortest Pokemon using Tablecloth. So the first thing that we do in this function is we use a thread first and macro, and then we send the Pokemon file path. It goes right into the data set, and the result of that will go into the select columns. Now, by the way, when I say TC, I mean Tablecloth, but I just didn't insert the import here just to save space. So Tablecloth, select columns. As you can see, you can put the names of the columns as keywords, and this is how you will get the relevant columns that you want. And last, order by. Pretty straightforward. What do I want to order it by? It's the height. That's it. Done. 3-4 lines of code. Amazing. This is the amount of code that I had to use in order to do the same thing with just Clojure. And again, maybe you can do it a bit better. Maybe you can do it a lot better. But still, compared with just those 3 functions that I got out of the box with Tablecloth, that's pretty amazing. Now, what will happen if I run this code into the REPL? The first thing that I want you all to notice is how beautifully this is printed to the REPL. I didn't need to use extra print function or anything like that. It's just being printed beautiful the way you see it over here. And the next thing that I want you to notice is there are empty values. Now, I chose to go with the default behavior of Tablecloth and just get those values as nil or 0. But if you want to do specific, if you want to do some other strategy for handling missing values, you can do that with any of those 3 functions that I listed over here in Tablecloth. You can do the select missing, you can do drop missing, maybe replace it with something else. So there you have it. Now, do you want to know what happened when I ran the Clojure code into the REPL? Yep, I got an error. And this error is because I had empty strings and I didn't handle that in my Clojure code. Now, okay, I think that you maybe kind of got the idea of the comparison between, just Clojure with Tablecloth code. And I just want to do another example with just Tablecloth, just so I can show you a few more actions that you can take with Tablecloth that are not as simple as what I showed you just now. So I decided that I want to find my matching Pokemon. And when I say my matching Pokemon, I mean by my height and weight. And I wanted to know how many wins this Pokemon had. So this is the code. Now, don't panic. We'll go through line by line. But before we do that, this is the import that I promised you. So when I say TC in this code, you remember that it's just the Tablecloth API. So let's go line by line. So in my Pokemon total win count, what we use to get the number of wins of a specific Pokemon is the Pokemon total wins count. So this is this def that we have right there in line number 1. So let's see what happens there. So in Pokemon total wins count, what we will be getting is a data set with 2 columns. One column will have the number of wins, and the other column will have the Pokedex ID of the Pokemon that we wanted. So the first step that we will do, you have it again, the dataset function that takes the Pokemon Combat's file path. Then what we do is group by, and over here we group by winner, and winner is the Pokedex ID of the winner Pokemon. And this is in order to have all of the lines that have a specific Pokédex ID grouped together. We use that in the next line, which is aggregate. And this is where we actually do the counting of how many lines of winnings this specific Pokemon had in each group. The last part of this def is rename columns. Now, the reason that I did that was because later on in line number 12, I am going to do a left join. And left join is being done by matching columns by their name. So in the combats table, the winner column was named winner. So I renamed it to Pokédex ID, so it will be easier for me to do the left join later on in line number 12. So now that we have you remember, we have two columns, one with the Pokédex ID, and the other has the total number of wins for each Pokemon. Let's see how many wins my Pokemon had. So again, we start by loading the Pokemon file, the Pokemon CSV file into a dataset. And then we have the select columns, in which we select 4 columns. We select the Pokédex ID, name, height, and weight. And then we have lines 10 and 11, where we do select rows. Now, what I do over here, I filter these rows with the predicate that you see over here in line number 11. And I ask, just by, is it my weight and my height? And this is the way I chose to do the filter. And then we have the left join that I talked about. This is in order to connect the two data sets, the one with all of the Pokemon data and the one with the total number of wins. We have order by, the amount of wins. And again, select columns, because we just don't need all of them. We just need these columns to be presented as the result. So are you hyped to see what Pokemon that matches my height and weight has the most wins, or not most wins, how many wins this Pokemon has? Okay. And ta-da, it's Hitmonchan. It's this, I think it's like super cute. I know I make myself laugh, but okay. I love the fact that like it has like the boxing gloves, but also the skirt. I kind of dig this vibe. So later on, I was curious which Pokemon has the most wins, and it's Hoot Hoot, which I don't know. I find it weird. I wouldn't bet on this to be the Pokemon with the most wins, but I'm not going to argue. Let's move forward to the real deal of this of this presentation. So now that we've seen how beautiful it is to write, data manipulation using Tablecloth. If that didn't convince you enough to start using Tablecloth today, tomorrow, yesterday, so if that did not convince you, let me try to show you the real magic behind Tablecloth. And I'm going to do that by doing a deep dive with some code examples. So what we're going to look at are 3 structures that you're going to find when you start using Tablecloth. You will use the data set, you will use row, and you will use a column. So when you start with Tablecloth, I think you're already familiar with this, strip of code. You will see the data set, Pokemon file path. You already know it. And we want to know, what is this data set structure? What is this? And that's what it is. Dataset is a special type which can be considered as a map of columns implemented around TechML data type library. So when I say a map of columns, does it mean that I can just refer to each column as a map? Let's see. So what is a data set? Over here, you can see that I defined the Pokemon DS. I use the get Pokemon DS function. And if I send it to the repo, we will just see the Pokemon dataset printed. Now, remember how I said that you don't need a print function and it's just printed out beautifully the way it is? That's that's it. You see, all of the columns are well ordered, and it's, the spaces are really nice, and it's super easy to look at it when you're working. Also, you can see the amount of lines and columns mentioned up here. And then I'm going to ask, so wait a minute, what did we say about dataset? Is it a map? So, yeah, true. That's a map. So what are the keys of this map? That's interesting. And I guess that you can kind of guess it because that's very intuitive. And yeah, you guessed it. The columns, the keys are the columns' names. But notice this, each and every one of those is actually a keyword, which means that yes, you can use them as just normal keywords in every Clojure map. And the values obviously will be just the values of each column. And I want you to notice that what you see over here is that each column holds the values as the basic types, like string, like int, and this is very efficient in terms of memory usage. There isn't like a very special object or something. It's just those basic types. So we can approach the data of a single column with a keyword. Yes, we can do that. So if I jump a little bit ahead, if I use the Pokédex number with the Pokemon DS dataset, then yeah, we got the column of the Pokédex number with all of its values. Now, this is pretty cool, but I promise that I'm going to show you what's behind that, not just a few simple code examples. So let's do just that. Because when I said that it's a map of columns, it's not really a map, just simple map of columns. It can be considered as. And I want to make this a little sharper. What does it really mean that it can be considered as? It means that there is a whole lot of things going, happening under the hood. So if we go directly to the Tabular dataset repo and we go to the dataset CLJ, we can see over here that the def type dataset is actually implementing Java util among other implementations that we have down there. Now this code is pretty long, so you can now understand that the beauty that we get, for as a user, as a developer, I get to use dataset as just a map. But the flexibility comes from having implementation of several other Java interfaces and Clojure protocols. So if we move forward to column deep dive, what we will see is that each column can be considered, remember the considered as again, named sequence of typed data. So if we go to the same place that we found the dataset CLJ, we will see column CLJ. And if we go over there, surprise, you will see that the def type of column is actually, it actually has a P2 array buffer. Now, here's the thing. When I said named sequence, maybe some of you thought, wait, like lazy sequence, like regular sequence? And the thing is that, and nothing here is just simple sequence or just simple map, because the efficiency comes from the usage of this array buffer. And let's see the example. So we will get it, just right in front of our eyes. So what I'm going to do over here is I'm going to create a big data set, which is constructed of 2 columns with 100 million rows. And you can see how fast this being loaded. I typed big column and it just brought back 100 million rows in mere seconds. And then what you can see is also that I asked for the 1 million row, and which also happened pretty quick. Now, in the last example, you can see that what I did is I used fun in order to multiply by 3 all of the rows in big column. And then I wanted to add 1 to all of the rows of big column. And then I just wanted the 1 million row. But here's the thing. if I would use lazy sequence, I would need to make 1 million computations because it will do all of the computations until the actual value that needs to be returned. In dtype next buffer, the only thing that was computed was multiply by 3 plus 1 once for the one value that I needed. Another cool thing that contributes to the high efficiency of this library is that it's lazy and non-caching. And when I say non-caching, by simple words, it's just not remembering anything. Now, sometimes it's good to have values that we already calculated to be remembered, to be cached, but it's not always like that. For example, if we do some image processing and we have a long pipeline of processing operations, then we maybe do some computation on one slice of the image. We don't really need to have this slice that was computed already saved because it's going down the line. So I think that's the beauty of lazy and non-caching. So let's move forward. And we got to the last part. We will talk about row deep dive, and there isn't a lot to say about this. I just wanted you to notice over here, again, you can see how I just dived into the TechML dataset, and I went straight to the do select rows. And what I found over there is that like in line number 400, it does select dataset or column all row indexes. And then I was like, wait a minute. So a row is a column or a map? Let's see for ourselves with this last small example that we have for today. So again, we still use the 100 million lines data set that I created. And over here, you can see that the first thing that I did was I asked to get the 3 first lines as the 3 first rows as maps. And what you can see is that it actually returned a map where the column name was just injected with the row value. And this way I can send these maps down the pipeline for other functions that are expecting, to get more of these internal maps in the big array that I have, or the big collection, not array. So that's pretty useful. And the next thing that I want to check out is this example. So over here, what I show you is me asking if this a map, like is a row, is it a map? I get true. But then when I ask for the type, we will see that we get a special type called fast struct, which is what enables us as users, again, developers, see rows as maps, but it's actually stored in columns. So yeah, rows are both, they can be considered as maps, but they are actually stored in columns, and it's special maps of type fast struct. So I can say we dived like pretty deep, but not that deep. If it's not deep enough for you, I invite you to dive even deeper with the Clojure study groups and, go find new things and learn more about Tablecloth and about TechML dataset. And you get to do that with great, great people. And if you want to join them, just scan this QR code and join the party. I'm telling you, you'll have a great time. If you ask yourself, okay, May, or I said, if you ask yourself, okay, May, but I guess you got the point. If you ask, what else can I do with Tablecloth? So, ta-da, that's the link to my previous talk about Tablecloth. And again, the QR code will take you there, and you will see in this talk that I go line by line with code examples of different functions that I found in the Tablecloth documentation. I just explained them and how to use them. And all links and code examples, they all can be found here in my GitHub or in the QR code if you manage to scan it. And we're almost done. But there is one thing that I have to do before you go. Are you all ready for this? I hope you are. I want to give big thanks to Daniel Slutsky, first of all, for being an amazing friend. But also, I want to say big thanks to Daniel Slutsky for helping me with this presentation, with the code examples, with thinking about how we can do this the best way possible to prove the world how beautiful and amazing Tablecloth is. And now is an amazing time to end this presentation and say thank you for watching and listening. Is this slide overwhelming? Yes, but I saved it for the end, so that's okay. All of these Pokemon, it's just the last slide. Thank you.
Thank you very much, May. Thank you very much. And to all our viewers, we have some issues with the sound, hence we've had some, it's like on our end. So we'll soon head over to Michael and his next presentation. Hence we can't do a Q&A because we have some issues with the sound here in the studio. Sorry for that. Again, thank you very much, May. There are big applause. People are shouting and cheering in the YouTube chat. Very well done. I think it was a very interesting presentation. I also would like to say that myself is pretty old, so I also only know the first generation of Pokémons, and I started watching Pokémon again with my kids, and we only got to the first generation. So, we are soon to get Michael on for his presentation, Intro to Rust. In the meantime, yay! Michael here. Welcome, Michael.
Thank you. I have no idea how I'm supposed to follow up a presentation that included Pokemon, Mario Maker, and Star Wars. That's just beyond me, but I will do my best. And just to check, it sounds like we are not going to have any kind of Q&A on this?
No, we have some issues with the sound. I'm sorry for that.
Okay, so normally this is a more interactive kind of presentation. So instead, I'll just talk at you. I hope it works. So everyone, hello, welcome. This is going to be an intro to Rust. My name is Michael Snoyman, also by chance hailing out of Israel, and happy to be speaking here today. Just a quick background on myself, perhaps a little bit relevant to understanding where this is going to be going. I've been a Haskell developer for 15 years and a Rust developer for about 6 years at this point. I bring a lot of that Haskell background with me, and we will be getting into that in this talk. I am the co-author of the Begin Rust book, and I wrote the Rust Crash Course, something that FP Complete provides, and I regularly do training on beginner and intermediate Rust and Haskell as well. My experience in the past few years has focused a lot on production apps in Rust, and it's kind of been all over the place. Back in servers, I've done a lot of blockchain work and smart contract work, building up CLIs, analytics tools, and more. So I'm going to try to pull in some of those concepts in this introduction. First question is, what is Rust? And I'm going to give the most bland explanation I can give you first, which is it's a systems programming language. It's a language designed to be a replacement or a competitor to C and C++. It doesn't have a garbage collector. You have complete manual memory management, and you have a very big focus on high performance in Rust. And with that kind of bland, boring introduction, you may be wondering, why exactly am I speaking about this at a functional programming meetup? Doesn't seem to make any sense. The interesting thing about Rust is that while it is a systems programming language, there are a lot of features in here that would be very interesting to functional programmers and application developers in general. Just to cherry pick some of the ideas, Rust has a very strong type system. And we'll get into what exactly a strong type system is, but it's a strong type system. If you're familiar with Haskell, it's very similar to the type system in Haskell, in fact. It is a memory-safe language, a language that doesn't allow for undefined behavior. And this is in stark contrast to, say, C or C++, which make it very easy to run into undefined behavior. And this is one of the big points drawing people in from the systems world into Rust, while still making application-level developers feel comfortable with the language. This is one that it took me a while to identify. Rust is an expression-oriented language. Now, that's not a surprise to people who know Rust. The thing that really caught me is I think this is where a lot of the functional feel of Rust comes from. We'll see what that looks like. There are a lot of influences from FP languages. As we get to iterators, that's one of those, that's a really powerful example of functional programming, but there are others. you will hear this phrase tossed around a lot, zero cost abstractions. And the idea here is you should be able to, in Rust, write high-level code, use nice abstractions that provide safety and convenience without paying a runtime performance penalty. There's a fun phrase also, fearless concurrency. Rust is one of the best languages out there, in my opinion, for writing concurrent code. Many of the bugs that you can typically run into, even cases like data races and deadlocks, these can be not completely prevented, but in many cases pushed away by the safety guarantees in the system. We are not going to get into some of those details today, but it's worth being aware of. Rust is also a language that has an amazing package manager out of the box. Cargo and the Crates ecosystem provide great packages, and we will be playing with a bunch of those packages today. And finally, Rust makes heavy usage of macros to avoid boilerplate, and we'll see some of these macros in play. The point of all this is that Rust is absolutely an amazing systems programming language. If you have to write an operating system, if you have to write a game, you have a real-time requirement embedded, sure, go ahead and use Rust. But don't be afraid to use it for application programming as well. In fact, all of the work that I've done in Rust would count as application programming, not systems programming. Because I am legally required to start off with a hello world, we'll start with hello world. And this example is exactly what you get out of the box if you just install the Rust tooling and type in cargo new project name. This is a very typical hello world, except there's a little bit of, this at least bothered me when I first started. Why is there an exclamation mark? It's just println. Why is that there? And normally I'd wait for answers, but we're going to skip over the me pausing, waiting for answers, and I'll just dive in. Rust, in this case, is actually using a macro. And it may feel a little overkill if you're coming from other languages. Why would you need a macro for something like this? And the idea is that println works with format strings. And these format strings are all compile time checked, and to a fairly nice extent, in fact. You can see it does syntax checks. If you have unbalanced braces, they don't work, checks that variables exist. It also checks, and this is starting to get into more of the type safety concepts, it also checks, is it actually possible to display this thing? This sum5 is an optional value, and there's no built-in display for optional values for good reason, which we just don't know how to display it necessarily. And so Rust will actually block you from being able to do this at compile time. This works because now we've turned on debug output and we know how to do a debug output for this. And you can also do some interpolation like this by putting the variable separately. Point being, even from the very first line of code that you see in Rust, convenience and safety are the first things you're really getting to see in this language. Cargo.toml is the file that we use to define our dependencies and a bunch of other things about our code. We are going to be using a bunch of, in fact, all of these libraries will get used in the slides that are coming. So I will make the slides available after this talk. And if you want to play around with this, you'll be able to copy and paste this and then use the code samples that I've provided. Okay. Oh, and also go to rustlang.org. Very easy to get set up. I will be doing some live coding in this, and I personally use VS Code with Rust Analyzer. It's a very nice combination of tooling. Okay. Let's start off by getting a basic flavor for what this language looks like. We're just going to play around with a few basic concepts, and then we'll be able to move on. So up here, we have a use statement. This is where you import things. And in this case, we are going to import the display trait from the std crate, and inside the std crate, the fmt module. And we use the double colon or time to namespace between these different aspects. Now we have display in scope, and we will be able to use that down below. This is where we define a struct. And if you come from a functional programming background, you may have heard terms like product and sum types before. I will define them briefly, but I'm not going to go into too much detail on this. Here I'm defining a staff member, and a staff member is going to have two fields. There's going to be a name, which is a string, and a job, which is a job type. This is the first place where I say Rust is awesome. Enum job. Enums in Rust are sum types. If you're familiar with Haskell like I am, you're used to the concept of an ADT, an algebraic data type. That's a kind of scary term, but the idea here is we are able to say a job is either a principal or a teacher. And if you happen to be a teacher, the teacher will come along with the subject. And the subject is also an enum, and that's going to be either history or physics. Now that we've defined our data types, I'm going to go ahead and start writing some code. So we start off in our main function. The main function is going to define a new staff variable, and this is how we construct one of these values. We use the staff constructor, we fill in the fields, we are going to call our staff member Alice, and Alice is going to be a physics teacher. And again, we use the double colon to do namespacing. We get access to these variants. That's the term we use for them in Rust. So teacher and physics are both variants of job and subject. And then Rust kind of has a little bit of an object-oriented flavor as well. So we are going to call the greet method on the staff. And this is how we define a greet method. We have this info block for staff. We are going to take a reference to self. We're not actually in this talk going to get a lot into ownership and references and borrowing, but that is arguably it is the core feature of Rust. The fact that we use ownership in order to avoid a lot of the memory safety bugs that can exist in other systems programming languages. It's arguably the most complicated thing you have to learn in Rust. And I would recommend, this is definitely something worth spending time learning. It pays a lot of dividends. But we're not going to get into that today because we're going to instead play with more fun aspects of the language. So inside our greet function, greet method, we now have access to self, and we can print out information on this person. So we're going to say, hello, name, your job is job. You might be wondering, how exactly does Rust know how to print out, well, name, fine, it's just a string. How does it know how to print out job? That's where the display trait comes in, and we'll get to that in a sec. The other way of doing this is you can actually do pattern matching and destructuring of data like this. And so if you come from another language that has pattern matching, you may be used to this concept. And the idea here is I am able to take some larger data type and break it down into its individual fields and then use these directly. Pattern matching is a very powerful feature. This is just scratching the surface. We'll see a few more examples below. Okay, but one of our questions was, how exactly do I know how to display this job? And that is where the display trait comes into play. If you're coming from an object-oriented background, traits are kind of like interfaces. If you're coming from a functional programming background, they're very similar or in many ways identical to type classes. And the display trait is a built-in part of the standard library, and it's used by the println macro. When we use this syntax for embedding a value, we are saying, please go off to the display trait and use that to display our value. And now inside here, inside the display impl, we are going to define a method, fmt, and fmt is going to be used for formatting these values. And once again, we are going to use pattern matching. So now that we have a job, we can see, is this a principal or is this a teacher? If you've never worked with a functional programming language that has the combination of sum types and pattern matching, I strongly recommend getting some experience with it. I use this all over the time in every code base I've worked in, and you'll see some more real world examples. I think I have some real world examples of this later on in the slides. So here I'm going to use another macro. Like I mentioned, Rust is a very, very macro friendly language. We're going to write principal into this formatter. And here I'm going to write the subject, teacher into this formatter. And same thing down here, just providing a display impl for subject. One other really cool thing, I mentioned zero cost abstractions. You may notice this doesn't say anything about writing to std out, doesn't say if it's writing to a file, doesn't say if it's writing to an in-memory buffer. This formatter abstraction allows you to write to all of these different data sinks, these destinations, very efficiently. So you can use the same method. Instead of printing out to std out, I could instead say this. And now toString is going to efficiently fill up a buffer in memory. And so again, you're able to reuse this code use it for multiple different purposes, and keep efficiency at the same time. Okay, so that is our quick basic flavor of the language. Now let's get into some more interesting things. Iterators. I throw this one in first for functional programming audiences because this is so similar to functional programming. This, again, I will copy this over to VS Code and we'll play with it here. This is a contrived example that I use very often. I want to go through the numbers 0 through 99. I want to take all of the multiples of 3, add 1 to all of them, and then take the values as long as they are less than 50 and print each one of these out. You could do this in other ways in Rust. You could use an explicit for loop. You could use a whole bunch of mutable code, the same way you would in C or C++, in JavaScript, or in lots of other languages. But this is the way that I would recommend you actually do it in real life. Here, we're using an iterator. This value here is not an array. It doesn't take up 100 values in memory. It doesn't allocate anything on the heap. Instead, it will efficiently create a data structure that will pop one value off at a time on demand. Each one of these iterator adapters, filter, map, and take while, will then perform some kind of an action on that stream of values coming from that iterator. And finally, our consumer function for each will take each one of those values that actually gets yielded from this entire iterator here, and then perform an action on it. In this case, the action we are going to perform is just printing out the number. Now, there are lots of other ways of doing this. You could, for example, you could do the whole thing with a for loop instead, and that works. I would argue it's slightly less elegant, but it might be more natural. The nice thing about this is the fact that iterators power every for loop that exists in Rust. And again, you get the zero cost abstraction idea. I want to be able to use an efficient iterator. I want to avoid allocating memory on the heap or allocating memory at all if I can. But I want to be able to use the common command structures like a loop that I'm already used to. So that's a very cool aspect of the language. Okay, let's talk about error handling. Rust is a language that does not have and doesn't believe in runtime exceptions. You could argue a little bit about this because Rust does have a concept called panicking, and panicking kind of, sort of, behaves like a runtime exception, but it's intended for catastrophic events. It's not intended for normal control flow in the application. Instead, in Rust, the recommendation is to use explicit errors and explicit error types. This is able to leverage the result data type, and this is one of those cool things in the language. Result is an enum. It is either okay or err. Those are the two possibilities. And basically every library, every tool, anything you're ever going to work with in the Rust ecosystem will end up using the same result for error handling. And this provides a very convenient way to handle things. One of the common issues you run into when doing error handling in other languages is it's easy to forget to handle the error. Common case, let's say that you are going to use printf in C. Technically, you are supposed to check the return code from printf every time you use it. Most people don't, but there's nothing in the compiler to enforce that. In Rust, there's a must-use pragma, and this must-use pragma can be put on data types to say, hey, if this value comes into existence, you have to do something to deal with it. And I'll show you what happens when you don't do that. And then on top of everything else, there are some great libraries to make working with errors much easier and make it possible to do good error handling. Anyhow, in this error are two different libraries that are commonly used. I'll be talking about Anyhow because it's the library I use the most, and I think is the one that especially people coming from an exception background are most used to. All right, let's look at this example. Our main function now returns a result. If this main function returns okay, which is what we see down here, then the program exits normally, no problem. But if it returns error, then the program is automatically going to return a failure status code and print out information on what went wrong. Going down here, I am now going to open up the file. So I'm using this helper create fs error, which provides very nice error messages when anything goes wrong with the file. I'm going to open this. You may notice this question mark at the end. This question mark says, if this expression fails, if it returns an error, return that error from this function. And so in many ways, you can kind of simulate runtime exceptions in your normal code. It's very terse syntax. And if I take it off and I save this file, nothing works. Because now our file is a different type. It's now a resulted file on error. There's no way for me to get access to that file without dealing with the error case. Now I could not use the question mark. Instead, I could use the same pattern matching we saw before. And I can say if it's a file, return a file. And if it's an error, I could do something like but the reality is what I'm implementing right now is more or less exactly what the compiler will build for me automatically just by using the question mark operator. So you get the benefit of if you want to be able to handle an error, it's very easy to do so. But in the very common case of I just want to propagate this back upstream, you can do that. Okay, now that I've got my file, I want to read lines out of the file. I have to use a buff reader adapter so that I have a buffered file reader because I'm about to read it line by line. And once again, we're able to see iterators come into play. Now that I have this buffered file, I can use the lines method to get an iterator, which will give me all of the individual lines in the file. And I will use enumerate to give me the line number. Now I get back a pair of the index, meaning which line in the file are we at, and the line. This is another interesting part of error handling. As you read more and more lines out of the file, it's entirely possible that a new error is going to occur, something that didn't occur when opening the file. And so Rust gives you a result at this point as well. Here, we do the very common approach of inside the for loop, go ahead and deal with the error, and if it's not there, get back a line. This bit here is a piece of code I would strongly recommend using when you're using Rust, which is context from anyhow. Oftentimes when you get error messages, you don't know where they're coming from. You can look at stack traces. Rust has the Rust backtrace environment variable to get better backtraces when an error happens, but it can be very convenient to be able to say something happened. This is a very simple kind of context saying something happened, but you can also build up more complex examples like this. And once again, we're using the same format strings that we've seen previously. Final thing on error handling before we move on is types matter. This Rust function, main, has to return a result. Since it returns a result, I can use the question mark operator throughout. If I take that off, question mark operator is no longer, and by the way, it's called the try operator. I keep calling it question mark, but it's called the try operator. Once I take off that return type, then main is supposed to return void or unit. If it's returning unit, you can't use question mark here because it doesn't make any sense. But since the function actually does return a result, I have to make sure that I do, in fact, return a result from the end. And this is what I'm doing here. This in particular is a really weird bit of Rust code, and I think it drives people crazy the first time they see it. The inner set of parentheses is the unit value, meaning nothing happened, kind of like void in many other programming languages. And then we wrap it up with OK. That's how we have that double nesting, what looks like double nesting of parentheses. OK, that is now good on scratching the surface for error handling. Let's move on to another bit of code. OK. Cool. So prime factors. This is going to be a somewhat complete bit of code. Complete with test suites, which, yes, I do occasionally write test suites. We have a helper function up here, read line. I kind of wish this was included in the standard library, but it isn't. And it's a little bit awkward doing this. Again, I kind of wish it was in the standard library. The idea here is we're going to create a new string. We're going to get the standard input handle, and then we are going to read a line of input from standard input into this mutable string. I'm not doing good error handling here. I'm just unwrapping and throwing away the error messages. If I was going to do this correctly, then I would instead use something like this, where I say there's actually a possibility that this thing can fail. We're ignoring errors for the moment, though. Okay. Now we're going to come to our main function. Oh, and I should actually run these things. There's no point using VS Code if I'm not actually going to run it. I'll remember to run this by the end. All right. So our main function, we want the user to give us an integer somewhere between 1 and the maximum possible U16 representation. We'll read that in from the input. In fact, I'll just show this working. Let's give it a cool number like 42. And it tells us the prime factors are 2, 3, and 7. Sure enough, 2 times 3 is 6, 6 times 7 is 42, so math works, the program works. Let's see how we implement this. So we'll take this input, we'll trim off any white space that comes in at the end, like the new line character, parse it, and once again, we'll just throw away the errors because we don't care about it in this case. Then we are going to use our prime factors function to get back a vector of all of the different factors. And then we can use the for loop to be able to iterate over this and print out all of the prime factors, which is exactly what you saw right here. Now we get into some fun Rust. How do we calculate the prime factors of a number? So we're going to start off with some input. We're going to make sure that it's not 0. And now we are going to keep track of the factors we've discovered. We're going to keep track of the prime numbers that we found and the current prime number that we're testing with. There are far more efficient ways to do this than the way I'm about to do it here. I went for simplicity here. There are much better algorithms for coming up with prime numbers, but efficiency wasn't really the point here. As long as input is not equal to 1, we need to keep going and find more prime factors. So if input modulus cur prime is equal to 0, that means that the current prime number does in fact divide into the input, and therefore it's one of the prime factors of the number. In that case, we will add the current prime as one of the factors, divide out input, input will now get reduced by the current prime. You'll notice, perhaps different if you're coming from a functional programming background like I am, mutability is right out of the box in Rust. Now, in order to be mutable, you have to declare your variables as mutable. It doesn't happen, the default is immutable, which is nice. If the current prime doesn't actually divide in though, instead, we want to calculate what the next prime is, push that onto the list of primes, and then keep going. And eventually, we will return all the factors at the end. Just for sake of time, I'm not going to go into all the details about next prime, not terribly interesting, but the code will be available later for anyone who wants to look at it. The next interesting thing is how we do tests in Rust. This is a very common way of setting it up. It's not technically necessary to put everything into its own module, but by convention, that's what we do. We say only build this if we're running the test suite. Here are the tests, and each one of them gets this little test attribute added to it. And these are standard unit tests, the way that I've written this here. So if you take the prime factors of 1, it should give you an empty vec. If you use these prime numbers, you should get back a singleton vec, and then just some arbitrary numbers. Very nice. But we can go further. And once again, if you are a functional programmer who's familiar with quick check and the property testing approach to things, you may like this. Quick check is a library which will allow us to write a function. The function is going to take some input, and quick check will generate random values and run this function 100 times, 1,000 times, whatever the default is, or however you want to override the default. And it will confirm that this property works. So here I'm saying, since we're not allowed to check against 0, I make sure that it's not 0. Otherwise, it confirms that if you take the prime factors of a number, and then you get the product of them, it comes back to the original, which is a pretty nice property test for something like finding prime factors. This little bit of code also demonstrates the functional nature of Rust. So here I've gotten the vec of prime factors, I convert it into an iterator, and right here I'm able to use the product method in order to construct a new value. Oftentimes we would look at this in other languages, in imperative languages, and use mutability to make this happen. This is another place where I definitely feel at home, like it's a functional programming language. Notice how this test has no mutability going on inside of it, and that makes me a big fan of it. Okay. Now let's branch out to some more interesting libraries. This one is called Cerdy. I think there are a number of different ways of pronouncing it. This is the way that I've standardized on, but might be wrong. The Cerdy stands for serialize and deserialize data. It has a derived system based off of macros, which we're going to look at. It makes it very easy to be able to serialize and deserialize data. Custom, different kinds of custom formats. There are many different formats supported out of the box, meaning if you go to crates and you look for Cerdy, or you just go to cerdy.rs, you will see JSON, YAML, CSV, TOML, message pack, and I think about a dozen other data formats that are all supported by Cerdy. So it's very nice to be able to just define your data types once and know that you will be able to use this for lots of different serialization formats. It's also leveraged extensively throughout the Rust ecosystem. So basically, I can't say everything that's going to do data serialization uses Cerdy, but all of the main libraries that I've ever used have had Cerdy support. Okay, so now let's go ahead and look at our example. Oh, you know what? I lied. I said I was going to, just on the previous slide, I'm going to run the test suite so everyone can see this thing actually run in practice. You can see it building all of the different dependencies. Oh, no, it failed. What did I do? Oh, multiply with overflow. Okay. Also something worth mentioning. If you, overflows or panics. So I write crappy code. Good to know. I'll have to look into that later. I don't remember what, I thought I tested this beforehand, but apparently not. Oh, changed it. Yeah, it's because I changed the code and didn't save. Okay. So now I feel a little better about myself. But that's the way that test suites get run in Rust. Okay. If I'm done interrupting myself, we will go back to this other example. It's Cerdy. We're going to be using anyhow again for error handling, and we're going to use the rand crate for getting some random numbers. And what I'm going to be doing here is I am going to define a data type called point, which is going to represent an XY coordinate. Why? Because it was the first thing I thought of. This here is all the work you need to do in order to make this thing work with Cerdy. We've said that I would like to automatically derive, serialize, and deserialize impulse for these two different traits. You can override a bunch of things. For example, I could say this should be X chord or something else, which looks pretty stupid, but I could do that if I wanted to. I'm not going to. We're just going to use the defaults here, but there are a bunch of attributes that you can use to customize the way that Cerdy serializes and deserializes. I use this extensively in the code that I write. Okay. Again, we are using an impl block like we saw previously. This is for providing a static method or a namespaced function called random. Random is just going to get a random number generator and then randomly generate a number between -500 and 500 for both the X and Y coordinates. Down here in the main function, we are going to notice the question marks again. I'm not going to comment on them anymore. We're going to open up a CSV file called points.csv. We're going to iterate through the numbers 1 through 100, 1 through 1,000, so just 1,000 times. And we will write a random point of data 1,000 times, flush it to disk, which technically isn't necessary. I like to do it. I like to be explicit about it. And then you can also put some information like this in the context, which can be very nice. And here I'm going to drop. Dropping, dropping is the core mechanism in Rust for handling ownership and ensuring that things get cleaned up. The main purpose for it is memory management, but it ends up getting used for many other things in Rust. In this case, we're using dropping to guarantee that the file handle gets closed at the right time. This kind of drop mechanism is used for other things, for example, locking a mutex and other kinds of concurrency issues, semaphores, RW locks, those kinds of things. So it ends up being a very powerful feature we get to use all over the place. Okay, now that we've written our data to disk, we can read it back. So we're going to use the CSV package again. We're going to open up points.csv a second time. We will use into deserialize. Into deserialize will give us an iterator of points, of result points, because there may be some kind of a parse error or an IO error. And then we will collect them back together. We collect into a result that does automatic error handling, short circuiting, and it will either give us back a vec of all the different points, or it will give us back an error message, and we can move on from there. Once we have this vec of points, writing it to either a JSON or a YAML file is trivial. Here I'm using ToWriter to give us a nice looking JSON file, or Cerdes ToWriter. Let's come in here, let's run this, and I can pop open these files and we can see what they look like. So you can see we do actually have CSV data, matching JSON data, and matching YAML data. If you want to use TOML, if you want to use message pack or anything else, pretty easy to be able to add that in as well. Okay. Let's keep going down the stack. I updated that. There we go. Command line tooling. There is a great library called Clap. If you're going to be writing command line tools in Rust, definitely recommend checking it out. And as you may notice as a theme, it uses macros, deriving, and attributes all over the place to make it very easy to define a command line interface. It also makes heavy usage of ADTs and sum types, product types, in order to make this work. So let's check it out. Close this again, close this again. So since ChatGPT is so popular right now, I decided let's do a chatbot, and we are going to have this set of options. This opt represents all the command line options. We can provide a chatbot, but you look up here at these attributes, and it says, well, you can specify this as a long option, which would be something like --chatbot name ChatGPT. We can also specify it as an environment variable and instead say chatbot name equals blah, something else. And we can have a default value. And the default value here is Eliza for anyone who's old enough to remember what that is. And then we have a clap subcommand. This is where the enums come into play. Because here I'm able to define a few different things I may want to do. And at this point, we may as well just run this. So say hello. Oops, didn't work because name is a required argument and we didn't provide it. So my name is Michael. Good afternoon, Michael. My name is Eliza. I can also say that the time should be morning. And it tells me good morning, which is nice. And I can say, what do I call that? Chatbot name. Equals Al. And that's very ominous. That's even worse. And of course, we can also do say goodbye, in which case we do not need a name or a time because it's not specified there. So right off the bat, this is pretty cool. You specify your data once, you get back nice, well-structured, well-typed data values. You don't have to worry about something failing. Once you get past the initial parse, all the data is simply there. It also takes advantage of existing traits in the Rust ecosystem. So I've specified time of day to be either morning, afternoon, or evening. How exactly did Rust know that I how to parse that and how to render that? Well, I told it. We have the trait called from string for parsing. We have the trait we saw before, display, for rendering. If this looks kind of tedious to have to write all this stuff out, there are helper crates for doing it. Personally, I haven't actually used those helper crates, that I probably should. But I also wanted to be able to show this off, what the code actually looks like in practice. So we've got display, we've got from str, and down here, in order to parse, this is all the work we do. We use the same pattern matching with destructuring right here, and then we're able to simply pattern match and decide what we want to do with this input. Okay, I think I'm running low on time at this point. I think we got about 6 minutes left. So I am going to move on to the last two examples. One of them is a web client. The async await ecosystem in Rust is awesome. Tokyo is the most popular library for working with this, and there are many add-on crates available in the ecosystem for working with a bunch of different things. One of them is Request. Request is a crate built on top of the lower level Hyper package, and it's used for making HTTP requests. And this is a nice little overview. This here, believe it or not, is a macro. This macro says, please run the main function with the Tokyo runtime. We build up a request client. You can set any kind of parameters. I'm being much more verbose here than we actually need to be. Request just provides a get method out of the box that we could have used, but I wanted to give you a little bit more of a real life example where you'd have to make some modifications. So we modify the user agent, and then with this client, we're able to get a URL, send the request. We use .await. This is the async await syntax that I was talking about. And as I mentioned, built-in Serity support, it will automatically use Serity for deserializing the data that comes back. We await again, and then we can print out our response. Just so everyone can see what this body looks like in the browser. It looks like this. And I've ignored a few of the fields, but I've defined our JSON response type down here. I've just stuck deserialize, and debug so that we can print this out very easily. And those fields, let's do that. Those fields simply get parsed directly. And so we end up with this kind of output. So with a relatively small amount of code and no work at deserializing, I was able to make an HTTPS request, get a JSON value, parse it, and print it out, which is kind of nice. And the final bit of code that we're going to look at today is a web server. There are a bunch of libraries in the Rust ecosystem. There is, why can't I think of Actix Web is very popular. Hyper, which is a lower level library, has a bunch of servers built on top of it. Warp is one of them. Axum is a relatively new library. I think it's been out for about 1.5 years now, maybe a little less. I've been using it extensively since then. I'm a very big fan of it, but I can't tell you that. I mean, but all the libraries are very nice. And let's see this in practice. So we'll start off at the main function. So our main function is going to use clap to get the command line arguments. Command line arguments here are going to say which host and port to bind to, get a socket address, and it's able to simply parse this or use the default value. Again, we're going to build up a request client. We'll see where that gets used in a second. We build up a router saying the different endpoints that we want to support. Already start running this program. And saying we want to provide a GET request using these 3 different functions. We bind the port, we serve our service, and we await because, again, this is part of Tokyo async and await. Just to give you an idea of looking at these functions up here, hello world just returns a static string, nothing interesting. Random number. Here, we are going to return a JSON representation of a random number. We will randomly generate it, shove it into this structure. We wrap it up with JSON and Axum, once again, built-in support for Serity and Serity JSON. And it will, in fact, when I do this right now, I probably can. And you can see each time I reload, it just gives me a different number. For completeness, there's hello world. And finally, because these are kind of boring, down here we have relay, which is going to use the same code we saw before to request this JSON value from HTTP bin. It's going to get the value back. It's going to return a JSON value, and we have to do error handling. And so we will return an error occurred value here. There are other ways to handle it, but that's the way that you can return different status codes. I kept it relatively simple here. And so if we go to the /relay, it'll take a little bit longer, and then we'll see the same JSON message that we saw previously. Okay. So tying up comparison, and especially comparison against Haskell, because that's what I'm most familiar with. In the style of FP, Rust has traits, ADTs. It's immutable by default. It uses strong typing, which I recognize is not a universal FP feature, but it is a Haskell feature. Iterators are very similar to lazy composition that you would see in Haskell. I know that other FP languages have other approaches to being able to stream data, and expression-oriented. We didn't actually see that much of the expression-oriented aspect of the language, but it's definitely there, and it's a pleasure to work with. Unlike FP, there's no garbage collection, and therefore you have to deal with ownership all over the place. My personal take is that for most application development, the benefits of the extra speed you get from garbage collection, or no garbage collection, probably isn't worth the ownership overhead you have to pay. But all the extra features you get in Rust, because of the way that the ownership system works, kind of makes it worthwhile, even though you are paying a little bit of an overhead as you start working with it. Over time, you get more used to dealing with ownership. Rust overall avoids more advanced techniques like higher kinded types. And in contrast to a language like Haskell, instead of having a general purpose notation like do notation, Rust prefers very specific notation like question mark for errors and .await for async await. Plenty of other use cases, but we're out of time at this point. So feel free to go through those. Sounds like we're not going to be doing a Q&A session, but if anyone has questions, feel free to hit me up on Twitter. I'm Snoyman on Twitter, and thank you very much for listening.
Thank you very much, Michael. Great presentation, and also a great introduction and presentation to Rust for functional programmers. And as you said, also all your material, you had like a lot of material. We'll link it and we'll put it into the description of the live stream so anyone can see it afterwards if they want to, check out, run the examples, etc. At this point, there's no questions. However, thank you very much for your participation. There's just like people are clapping in the chat, so they're like happy. Thank you very much. Very, very nice presentation. And with that, we will head over to Paul. Welcome, Paul.
Thank you very much. How are you? So, have we got there we go. Okay. So this is a presentation about Darklang. Darklang is a functional programming language that is built specifically for the cloud. So we designed a language which doesn't really live on your local computer. And a large part of that was it being functional. So we're gonna talk a lot about that. I understand there's no Q&A at the end, so feel free to drop your questions into the chat. I'll be keeping an eye on it, and I'll answer it at an appropriate time, possibly immediately when you paste it. But feel free to go for it at any point. So we're going to talk about why we created Darklang. I'm going to give a demo of Darklang and an overview of its main features. I'm going to talk about functional programming. I'm going to talk about a recent rewrite that we had that was from one functional language to another. And we're going to talk about where the project is now, and also a new secret exciting thing at the end. So about me, I previously did a PhD in compilers and static analysis, and then 2011 to 2015, I was the CEO of Circle CI. Took it from, sort of nothing to, about a couple $1 million, a couple thousand customers, that sort of thing. And then since 2017, I've been at Darklang first as the CTO, and then since 2020 as the CEO. I'll be talking a little bit about that later. So the reason that we're building Darklang, the sort of vision behind it, or the mission behind it, is removing accidental complexity. And accidental complexity, if you've read The Mythical Man Month, you might be familiar with this term. The idea is that you can split the work that you have to do into essential complexity and accidental complexity, and that the accidental complexity is sort of the bullshit that you feel you shouldn't have to do, but that you need to do anyway because computers, code, all that sort of thing. And the essential complexity is the kind of the core, the business logic, the kind of the central stuff that you're actually trying to do. And the idea of doing this came out from when we're at Circle CI. We're looking at building internal tools, and we realized just how much work would go into building internal tools, and how much of an extra product it would be, how much maintenance they would require, how much infrastructure, hosting, security, et cetera, would require to build internal tooling. And it really sort of caused us to do it a lot less than we really should have, and a lot less than would be valuable. So theoretically, the essential complexity of an application is just receiving data, processing data, storing and querying data, and sending data. And these are these are kind of the core of almost every application. I mean, it's very vague, but the core of every application, certainly every web application, the core of every programming language, this is really what it's about. Think of Unix applications. They receive data from standard in, process it, and write files and send data out. Like this is kind of the core of computation. It's kind of all the same when you think about it. But the essential complexity of what people actually want is the user presses send message, and then the message gets delivered. So everything below that, to a certain extent, is could be thought of accidental complexity. And this is sort of a more realistic essential complexity. It's sort of the business logic of how people actually think about their applications. So we're really trying to get to trying to raise the abstraction of programming, so that it becomes a lot more like this. And where it actually is today, this is the Cloud Native Computing Foundation landscape, and this is all the products and tools that are part of building cloud native applications. Cloud native, obviously, it's sort of a synonym for Kubernetes, but really, like these are kind of, when you're building applications in the cloud, there's an awful lot of steps, and you need far more tools than you really should. And so we're kind of where we started from this is saying, what if we don't need any of this at all? What if there's just one tool and it's relatively simple? And the other way that we came to this was looking at what it takes to get code into production. So if you write code on your machine, and you then want to put code to your users, there's a 40-step CI/CD pipeline, and it's not just CI/CD. We're including the actual deployment step here. We're including the the changes and the commits and the pull requests and that sort of thing. But this entire process of going from code in your machine into code in production is significant, is quite large. So we're really focused on, like, these are low-hanging fruit. How can we make these as simple as possible? So I'll give you a quick demo of building a very simple application in Dark. So we're going to build a HTTP handler. Oh, and I need to log in. So we are building a HTTP handler, and we're just going to do, a simple hello world handler where we say hello world. And I'm now going to open it in a new tab, and you can see here, this is, live on the internet, live on the World Wide Web, having the response that we put in it. And that was all that it took. There's no compiling, there's no making containers, there's no deployment, there's no serverless, there's nothing at all. It's just like literally every keystroke that we type is in production, and refresh it again. Here it is. And so, the very simple part is that you can do that, but we're going to do a little bit more than that. So we're going to make it, we're going to store something in the database. So we're going to make it so that you can say hello user, let's say hello Paul. And this fails obviously because there's no code here. We deleted it. In practice, you would do this slightly differently. We have tools around slow, safe deployments, but I'm ignoring them for the fast demo right now. So here I'm just going to say hello user. And we include the username. And then we'll open that tab here. What did I do to that? Oh yeah, need to actually put this into it. And then hello user Paul. Okay, that's wrong. So let's go back and we'll put a space in there. There we go. Okay. And what we are going to do is we are going to just do a simple data store. So we're going to make a simple data store, and we are going to store the user in it, and the user, we're just going to store user of type string. And then we are going to call this users. And we're just going to make it so that the users who visit are stored in the data store. So here we are going to just do extremely simple DB set. The value in the dictionary is going to be the same shape as the user. We put this alongside it. So we're just going to put user. And then we're going to have a key, which is going to be the username, and then it's going to be stored in the tables. So this is users. So this is basically what it takes to store data in a data store. There's no creating an SQL database. There's no SQL of any sort. There's no provisioning any sort of data store. The data store gets created automatically. So really there's we're looking at, and this is just a very simple example. I'm not going to go any further, make a real application out of it. But this is sort of the lowest level, simplest tools, and we have reduced the creation of the infrastructure and the deployment of the code and the infrastructure to basically zero. And that's sort of the foundations of how we do this. And so these are two of the main Darklang features. One is called, the first one we call invisible infrastructure, which is just sort of a degree beyond serverless. It's that not just are there only servers, but that there's not even the visibility of a server. You don't really think about things in terms of infrastructure. And this is sort of what I meant at the start by a functional language for the cloud. The language, in a sense, lives above the cloud instead of being, the cloud being a thing that is built up of servers and infrastructure, and the programming language being an application that runs on a Unix machine that gets put into a container that gets deployed to that cloud. Instead, the language is just sort of a layer sitting on top of the cloud, and you don't really think about its, about where this is running or how this is running. You don't need to think about that stuff. The second feature I showed you is what we call deployless. This is the instant deployments, and it's everything from sort of zero downtime data store migrations, the instant deployment nature, but a lot of tools to ensure that this is safe. So tools including feature flags, and the aforementioned database migrations. Those are kind of all part of what we call deployless. And the third one is trace-driven development. So you probably saw when we were opening, when we opened the tab in our browser, those live values were fed back into the editor, and we could see them. We could see like the values of the data store and that sort of thing, which I didn't really get into. But that's kind of the other core feature, the trace-driven development. So Let's talk a little bit more about the invisible infrastructure. You know, we're putting that idea of invisible infrastructure against the previous idea. You know, this previous idea that you would take a set of tools, you would deploy them, you'd buy them from your cloud vendor, you'd buy them from another vendor, and you'd build your applications on top of these like low-level tools where you needed to either orchestrate them together or you needed to, you know, pull them together with various different SDKs, and each of them speaks a different language. Each of them, you know, your database might speak SQL, your Redis might speak, well, does speak its own language. You know, Kafka speaks its own language. So if you wanted queues or caching or data stores or whatever it is, you would build them with different applications, which create a sort of impedance mismatch between your language and the data and the way that that data is stored. And in Dark, you know, these are the full list of components. We have a data store, we have cron, we have workers, or you know, backend queue worker. We have what we call REPLs that are just, you know, little tools that if you have a scripts directory where you've written a lot of bash, you know, it's sort of the replacement for that. And of course HTTP handlers, and these are the core aspects of Dark. And so you can sort of think of this as a replacement of whatever infrastructure is below that. You don't know, you know, whether it's Postgres or Bigtable or whatever behind the users table. You don't know where the server, where the HTTP servers are running. You're not aware, and in particular, you don't have to think of exactly how your HTTP servers are running and what load balancers they connect to, and how, you know, to carefully do the dance of switching from one, you know, backend deployment to another deployment. This is all sort of done. And same with cron and queue workers. You don't have to think about Kafka, and in particular, you don't have to think about the structure of the data that goes into each of these. There's no serialization involved. You just put a data into your worker and it's there and it comes out the other end. You put data into the data store and it is, you know, the built-in canonical format of the language. You don't have to think about, you know, what the exact formats of a Postgres table are, and how they map to your language, and whether you have 64-bit ints and Postgres has, you know, 48 digits of integers, and you know how exactly that all intersects. So that's what we've been referring to as this invisible infrastructure. No provisioning, no infra, no configuring, and in particular, no waiting to get code out there. It simply lives. You know, the code itself lives in the cloud. It lives on our in our database. It's accessible via our editor. There's no Git, there's no GitHub. All of these, you know, sort of any complexity that comes from that and any learning that you need to do, all that information that you have in your head about how Git works, you know, maybe someday you'll be able to forget it and no longer think about that. And this here is how we like to think about applications. This is not actually part of the product. It is our sort of a future version of how we want the product to work. And the idea here is that rather than looking at your product as a collection of files on disk, as a collection of, you know, sort of files and folders and functions within that, or handlers within that, we want people to think of their systems as a live application with traffic overlaid in the sort of directory, in what would be a file system or a set of directories. You know, we want you to be able to look at the actual endpoints of the data stores and the grouping of them, and be able to zoom in or out on the actual, you know, on the actual application itself. And what we modeled this on is when you start a new job and the senior engineer takes you aside and takes you to a whiteboard and starts to draw the architecture of the application, it's always, you know, it's boxes and it's lines between them, and this is what the data store does, and these are the important systems and components. And that's how we kind of want to model applications in Dark and what it means to build applications in Dark. And so this is sort of like our futuristic rendering of where we're going with that. Okay, so that's infrastructure. or invisible infrastructure. And the second big thing is deployless. And I talked about how this, this is the step involved in getting code into production. You actually make the change over in the top left, and then you make a pull request and do local code review and a local CI run. And then after it gets, there might be several cycles of that as you get reviews, and then it gets merged into the master branch, and then you do the same thing again, but maybe there's also integration tests and building a container, pushing things to a CDN, updating Kubernetes. And then as we get to the top right, we're actually doing the deployment and we're waiting for that to happen. And then we also enable the feature with a feature flag if you are doing that sort of thing, which you should do. And then in order to remove the feature flag, we go right back to the start and we do a whole sort of, the whole kind of process again. And so we want to reduce that to basically the essential complexity of what it takes to do a deployment of getting code out in production. So you make the changes behind a feature flag live in production. You can run an integration test if you want. You can get a code review if you want. So you can do that iteration in a much tighter loop. And then the actual deployment of it is just enabling feature flags. So as I mentioned, feature flags are part of the Dark application. And so you can enable feature flag, first enable it for your team and then roll it out to 10%, 50% or whatever. And then when it's done, you just sort of tick a box and the feature flag is done. You don't have to go through a whole new pull request, set of commits, a set of code review, et cetera, to be able to remove that feature flag. And in a sense, we're rolling a bunch of different parts of building applications into a single concept, the feature flag. So branches, development environments or different environments, and the existing feature flags and A/B tests, those are all sort of rolled into the single feature flag concept. So where there aren't separate, there isn't a dev environment and the staging environment. Instead, what there is the same stuff running in production with a feature flag hiding it from, and sort of creating that separate environment using the feature flags. So what you get from this, of course, changes are instant. There's no deployment, no CI/CD, again, no GitHub, no file system. And it also, both these features that we talked about, this deployment and this invisible infrastructure, are enablers of our third big feature, which is trace-driven development. So trace-driven development is the idea that when you get a request made in production, it is immediately shown to you in your editor, and it is the live production values that are shown in your editor. So there's this is sort of a bit of a deep dive into it. This is a FizzBuzz endpoint, and it does a FizzBuzz taking the word that's provided in. So you can see that in the middle there, request.params.name. And what you can see in this, there's a bunch of different things. So you can see where the cursor is on the letter I. You can see there that the value of I is 10 on the last iteration of this. So it's going from the range 1 to 10. You can see as well the bits of code that were executed in this trace. So for this iteration of map, which uses I is 10, you can see the if statement that runs, you can see the then, you can see that buzz is going to be the result, and you can see that the other stuff isn't executed and is faded a little bit to indicate that it isn't executed. And then finally, of course, you can see the result of the trace. And you can see that, this is 1, 2 fizz. And as you change the code, that updates, even without having to run it again. And that's sort of the idea of trace-driven development. And you can see there's, things like it replaces a debugger in the old days, or in how we code today. If you want to debug something, then you need to run it again. You need to either re-enable it with the debugger and then get it to the same state as you're trying to introspect, and possibly you need to build a minimal test case in order to do this, or at least a repeatable test case in order to do this. Or because that's difficult, often what people do is they just recompile their code with a lot of printfs run through it, run it, and then start to grep or search through the printfs to try and see what happened. And essentially Dark is both of these things. You get to see the value at every single variable at every single point, just like a debugger, just like you would in a debugger, but without having to restart it, without having to rerun it, without having to make a minimal test case, because you can use the actual request that came through the system in order to do it. And we found that this trace-driven development idea, this is something that people just absolutely love about the system. And obviously a lot of building Dark is done outside of Dark, and is at the moment it's built in F#. So whenever I'm using F#, I just really miss this. I end up doing some printf debugging, some running a debugger. But what I really want is when I ran that code, put my cursor on something and to see the actual value that it was as it went through the system. That's that's one of the most powerful things in the system, and it's enabled by the other parts of the feature. So this only works because we have the editor. It only works because we have our own programming language, and because the requests are running through our servers. We're able to combine all of these things to be able to make it work. So that's sort of the main features of Dark and the demo and why we built it and that sort of thing. And now I want to talk, I believe, about functional programming. So why is Dark a functional programming language? What is it specifically, or what is it like relative to other functional programming languages? So I've been using functional programming in production since about 2011. Circle CI was written in Clojure. Obviously, before that, I had written some OCaml and some Haskell as I was doing my PhD. And since I'd also written a bunch of Elm, and since we started Dark, that was originally written in OCaml and is currently written in F#. So I've really done sort of a trip through every statically typed and also Clojure. So quite a lot of functional programming languages. And so we've taken what I feel is the best aspects of it. I know not everyone agrees with strong static types. I'm a real believer in it. I think that static types are extremely important to making code that scales well, and that is understandable. But we have options and results, static types, first-class functions. Immutable data, I think, is one of the greatest things about functional programming languages. People don't really talk about immutable data as being an important feature of functional programming languages. I don't really understand why that is, because I think it's probably the best feature of it, or maybe tied for the best feature with static types and ADTs or some types. And so Dark also has impure functions. And in fact, we delineate specifically between what is a pure function and what is an impure function, because that's an important part of the trace-driven development. Pure functions don't need to be traced. Impure functions, we store the results of it on the platform, so that when you're in the editor and you want to see a trace of an impure function, whether that's like storing something in the database or making a HTTP request or simply like running date.now, those impure functions are kind of a key part of making trace-driven development, and the immutable data and the pure functions are the other key part of this of trace-driven development, because it allows us to rerun code in the browser / editor. As you make changes to your code, you can see what the new versions would be, and that's possible partially because we know exactly what's pure and what's not pure. So the initial influence on Dark was Clojure, and in particular, we really modeled Dark on what Clojure calls threading, what most languages call pipes. The idea of taking data and running it through a set of different steps, and that, I feel, gives people a really easy way to reason about applications. And I think that for functional programming, it's something that's sort of missing in or functional programming, I feel, would be relatively unpleasant without it. One of the things that imperative programming has that works really nicely, or that object-oriented programming has really nicely, is method chaining, the idea that you can do A.B.C.D. And I feel that that's what pipelining brings to Dark, and I first experienced this in Clojure and saw just how powerful it could be. It's also an Elm, obviously, and Darklang is very, very similar to Elm. It has that impurity, and obviously it's for the back end, not just JavaScript. But it is a very similar language to Elm. It's a very similar language to OCaml, which very similar to Elm. The first version of Dark was built, well, maybe the second version of Dark was built in OCaml on the back end and Elm on the front end. And while we didn't like OCaml syntax, and there's a lot of sort of cruft to this language, which sort of dates back to the late 90s, we tried to cut away on sort of the object cruft and really focus on the ML side of that. It's very similar, again, to Rescript. No surprise, since Rescript is based on OCaml, and it has a lot of overlap, as Michael was talking about before, has a lot of overlap with Rust, but obviously it is a little bit more functional, a little bit less imperative, maybe significantly less imperative than Rust, and of course is garbage collected, which I personally feel is an essential part of developer productivity. And obviously, Rust has gotten a different way, one which has sort of made Rust not my language of choice. Well, obviously Dark is my language of choice, but Dark, the current version of Dark, is built in F#. And so Darklang is a little bit like F# if we cut out the .NET interaction and the C# interoperability, which is an essential part of F#, but is obviously not needed in a language where the interoperability is mostly done via the via HTTP. So I don't remember what this slide is for. Maybe I was just going to talk about it. I've done that. Okay, great. So that's the language, and that's the functional programming aspects of it. So finally, I want to talk about, well, penultimately, I want to talk about the status of Darklang. So Dark, in 2017, Dark was a hot new startup. In 2020, we didn't quite land it at the right point, and 2020 happened, and so there was a big oh shit moment, and split up my co-founder, and the had to lay off the team, and sort of went down to just me as we had run almost to the end of the cash that we had. And so we've really been a transition since then. In 2021, I did a rewrite in F#. In 2022, focused a lot on enabling the community to see everything that we were doing, making sure that everything was published on our blog, and that started doing a bunch of Twitch and that sort of thing. And 2023 is going to be the secret new thing, which I'm actually going to tell you right now what that secret new thing is. Briefly, before I do that, we did a quick backend rewrite at one point. It was originally written in OCaml. We wanted it to basically be bug for bug compatible, and so we experimented with rewriting it in Rust. I did about 2 months of experimenting in Rust. Did not like essentially how imperative Rust was, and how low level it was, and kind of what you had to do to dodge the garbage collector. So ended up choosing to rewrite it in F# instead. That was supposed to take about 6 months, ended up taking about 20 months. But we ended up doing the transition over to the new system mid-June last year, and Dark is now fully written in F#. Is F# good? F# is excellent. It is really a beautiful language. Probably my favorite programming language apart from Dark, and is definitely my favorite functional language apart from Dark. It is a really beautiful language with an excellent type system, and it is a little bbit slow to compile, especially relative to something like OCaml, which is lightning fast to compile. And the .NET stack, the .NET web stack, is a little bit odd if you have a functional programming mindset, but once you get past that, .NET is great, moving very quickly, getting faster and better all the time. And you might not know this, .NET is open source, F# is open source, so these are great, sort of like foundational languages to build, and highly recommend it. for people. So the new secret thing that we are talking about, we've been like relatively public about this in the sense that people who are, on our, check into our Discord, or people who are people who follow our repo, which is public, can have been able to see what it is that we're doing. But and it should surprise absolutely nobody that we are starting to look at, or in fact, we are investing deeply and switching almost entirely the project to be something which is focused on how people write code using AI. And what I mean specifically there is that I don't really think that that writing code by hand is going to survive now that the AI has gotten not excellent at writing code, certainly not perfect, but has gotten like very good. And I think that we're, as someone who is working on an editor and a system of writing code, it really felt like the writing was on the wall, and that we were investing our time in the wrong place. So we actually, have made a big switchover and a big changeover to figuring out what is the best way of writing Darklang code using large language models, not specifically ChatGPT, but something along those lines, and to sort of to allow people to write code as quickly as possible, and still have the advantages of Dark, the invisible infrastructure, the deployless nature, the trace-driven development. We think that those are a really strong addition to the large language model generated code, or the AI generated code. But we are definitely early in our journey with that. We're gonna see where it ends up. So yeah, that's it. That's what we ran through. Talked about the main features of Dark, how we think about functional programming in Dark, and of course the new secret exciting thing, the AI driven writing code. So yeah, thank you for coming along with the journey. Very much appreciate it.
Paul, very interesting presentation. It was really cool I think that a lot of things and concepts you touched upon in your presentation is really kind of what I experienced myself with the projects you described, and how you write on the you write on the whiteboard and explain all the projects and why do everyone do this, and then all the slides you have, or all the slide you had with all like these different cloud solutions and whatnot. It's like at some point it has to evolve upwards. We can't be not one more solution for the cloud, not one more tool. We need to like get away from that and get productive again, not get bogged down with like the next cool Kafka version or whatever. And of course, I mean, looking at what ChatGPT and other tools in the natural language processing is doing, it is a matter of time before you can start doing more advanced, much more coding with using an AI. I'm looking in the chat. There's no questions. Just a lot of applause. So again, thank you very much, Paul, for your participation. Thank you. Yes, thanks, Paul. And as always, we'll put out all the sources and everything that Paul described below in the description of the video. So that was all for tonight. And again, we're sorry for the sound, and we'll fix that for the next time so we can do a proper Q&A with all our presenters. So thank you very much for tonight, and have a lovely day or evening, dependent on where you are. Bye, everyone.